Slide a block across a table, and it inevitably grinds to a halt. Throw a wrench in the vacuum of space, and it will glide forever. Here on Earth, an invisible thief called friction constantly steals motion, masking how the universe actually works. Because of this constant earthly friction, early scientists logically deduced that absolute rest was the final state of all objects. They assumed things only moved if you continually pushed them. Philosophers like Aristotle built entire frameworks around this idea. They observed carts and arrows slowing down, but failed to identify the unseen forces pulling the brakes. Newton's first law corrected this by identifying two natural states for any object, remaining at rest or moving at a constant speed in a straight line. Whether a parked car, a vehicle cruising uniformly, or a falling paratrooper where air resistance matches gravity's pull, the physical condition is the same. The sum of all external forces cancels to zero. Inertia itself isn't a force you can measure. It is nature's inherent stubbornness. An object will refuse to change its current state of motion unless an unbalanced external force forces it to. If a net force of zero maintains a constant state, we have to calculate what happens the moment those forces unbalance. Newton's second law dictates that an unbalanced force forces a change in velocity. Any change in velocity, whether speeding up or slowing down, produces acceleration. Force equals mass times acceleration. Look at this 100-kilogram car and 200-kilogram truck. If we apply 200 newtons to both, which accelerates faster? Pause and calculate. Solved. The car speeds up at 2 meters per second squared, while the heavier truck accelerates at 1. The math proves that acceleration is inversely proportional to mass. Because mass is a physical measure of inertia, the heavier an object is, the more fiercely it resists a change to its state. Newton's second law provides a deeper measurement of force by tracking an object's momentum, the product of its mass and velocity. When we calculate force, we are measuring the rate at which that momentum changes over time. We feel this time variable physically. It is the reason a cricketer pulls their hands back to catch a high-speed ball without breaking fingers, and why falling on a mattress hurts far less than hitting concrete. In the momentum formula, if a fast ball hits rigid hands, momentum drops instantly. Because time is a microscopic fraction, force skyrockets. But watch, if the catcher pulls their hands back, stretching the impact duration, the force shrinks proportionately. More time means less force. Manipulating time is how we survive extreme physics. Whether deploying an airbag or using a parachute, extending the duration of an impact is the reliable physical method for reducing destructive force. This brings us to Newton's third law of motion. Physical interactions always generate forces in pairs. For every action, there is an equal and opposite reaction. Let's test this with a classic problem. Earth's gravity pulls an apple downward, but does the tiny apple pull the massive Earth up with the exact same amount of force? The answer is yes. The force exerted on the apple is mathematically identical to the force exerted on the Earth. We apply the second law to see why the planet doesn't hurtle upwards. The forces are identical, but because the Earth's mass is astronomically huge, its resulting acceleration is practically zero. The apple has a tiny mass, so it experiences a massive acceleration. The universe operates on a strictly balanced ledger. Every push or pull you exert on the physical world is simultaneously felt by you in reverse, regardless of the size disparity between the objects. If every action triggers an equal opposite reaction, we face a logical hurdle. Why don't these opposing forces simply cancel out to zero, freezing all movement across the universe? Consider a book resting on a table. In this diagram, gravity pulls the book down, and the table pushes the book up with an equal normal force. But are these two forces an action-reaction pair? No, they are not. The vital rule of the third law is that action-reaction pairs must act on entirely different objects. In this case, both forces are acting on the book alone. Here are the true pairs mapping the interaction. The Earth pulls the book down, so the book pulls the Earth up. At the same time, the book pushes down on the table, and the table pushes up on the book. Here is your complete framework. First law: when the net force is 0, you get constant velocity or absolute rest. Second law: when the net force is not 0, you get acceleration. Third law: forces always occur in equal and opposite pairs, but they act on different bodies. Internalizing these 3 specific rules provides a framework to map physical interactions across the universe, turning chaotic motion into predictable math. Keep practicing with these principles, and you'll see the physical world clearly.